Okay, ladies and gentlemen, let us move on to the next mathematical problem. Let us mark it as example 3, where we are required to find the exponential Fourier series expansion of the given signal and also its power density spectrum. Now let's see the signal, which is like this. It is a rectangular signal. All of them having an amplitude of A. Mark it as x of t. This acts as t. This is 0. This is the negative time period Tp, positive time period Tp. And the pulse width, this is negative of tau over 2. This is positive of tau over 2. Now let's go into the solution. First of all, we'd like to evaluate the Fourier series coefficient for k equals to 0. For k equals to 0, evaluating the Fourier series coefficient and instead of taking the limit 0 to Tp, which is the time period in this case, we shall be taking the limit minus Tp by 2 to Tp by 2. So instead of taking the limit from 0 to Tp of the integral, in this case we will take the limit from negative Tp over 2 to positive Tp over 2, which is essentially the same thing. This works for one period and this works for one period as well. So C naught, since k equals 0, becomes 1 over Tp, the time period. The limit, as we have defined, goes from negative Tp over 2 to a positive Tp over 2. X of t, the signal dt, which equals 1 over Tp. Now the limit is changed to minus tau over 2 to positive tau over 2. And this is because since this is Tp, 0 to Tp, this point is negative Tp over 2 and this point is positive Tp over 2. Now, as you can see, from negative Tp over 2 to negative tau over 2, the signal is 0. So no need to integrate for this part. Similarly, we don't need to integrate for this part as well. Hence, we can reduce our limit from minus tau by 2 to positive tau by 2. Hence, we have changed the limit from minus tau by 2 to the positive of tau by 2. And the signal in itself, x of t, which is A, that means for every point from 0 to tau by 2, the signal value is A. A dt. Now taking A constant out of the integral, as it does not depend on the time, integrating dt we get t, and putting on the limit tau over 2 to negative tau over 2, we get a tau over 2 plus tau over 2 by Tp, which is a tau p. Now, if you notice, I haven't written the exponential term over here, because whatever you put in the value of k over here, e to the power something here, if k equals 0, this becomes 0, and this consequently shall become 1. So we can avoid it in this case. Now, evaluating for k when it's not equal to 0, we get c of k 1 over Tp minus tau by 2 to tau by 2. The function is a e to the power minus j twice pi f naught, or in this case you can write it as omega naught as well, but we shall be continuing with twice pi f naught t of k. See, I was talking about this term. Since k equals 0 in this expression, so this whole expression becomes e to the power 0 and consequently 1. So multiplying x of t with 1 will result in x of t, and we can eventually avoid this term. And the integrand is integrated with respect to d of t. So since a is not dependent on the integral, we take it outside of the integral. Becomes a over Tp, the limit minus tau by 2 to tau by 2, e to the power minus j 2 pi f naught t of k dt. So solving this integral, c of k becomes a over Tp, as we have seen many times. Integrating e to the power something results in the same thing, that is e to the power something minus j 2 pi f naught k of t, and the remaining factor that is not helping in the integration is denoted as the new denominator, twice by f naught of k tau by 2 to negative of tau by 2. Now, upon replacing the limits and solving, we get c of k to be a over Tp e to the power minus j twice pi f naught k tau by 2 minus e to the power minus twice pi f naught k negative tau by 2. These are both the limits, and the denominator, since it does not depend on the integration factor, remains the same, twice pi f naught k. Upon further simplification, we can write a over Tp, I mean cancelling this 2 and this 2, this 2 and this 2, the expression becomes e to the power minus j pi f naught k tau minus of e to the power j twice pi f naught k tau, and the denominator, you have guessed right, remains the same. Now, replacing this negative sign, I mean multiplying the numerator and denominator with a negative of 1, we get a over tp e to the power j twice by f naught k tau minus e to the power minus j twice by f naught k tau, and the denominator becomes j of twice by f naught k. And what I have done is multiplied the denominator and the numerator by negative of 1. Okay, now the expression can finally be written as ck, which equals a pi f naught k tp e to the power j pi k f naught tau minus e to the power minus j pi k f naught tau over twice j. Now I have changed the expression from this to this for a reason, and we'll come to it later. Before that, let us go and write down the Fourier series expansion, which is x of t equals summation of k, which goes from minus infinity to infinity, a of pi f naught k tp e to the power j pi f naught tau over twice j minus e to the power j pi k f naught tau over twice j and e to the power j 2 pi k f naught tau, minus. Now, in order to determine the power density spectrum, we have to work with C of k and determining the power density spectrum. C of k, which was given as a of pi f naught k tp e to the power j pi f naught tau over twice j minus e to the power twice pi k f naught tau can be written as something like this: a over pi f naught k tp. This is an expression from the Euler expression, that is sine of this crazy term, because in the previous maths we have seen sine of theta, which equals e to the power j theta minus e to the power minus j theta over twice j. Now, if we do a bit line more, multiplying the numerator and denominator with tau, we get a tau by tp and sine of pi k f naught tau over pi f naught k tau. So this tau and this tau cancels out and we go back to the previous expression. Now, why this has been done for? Because for this expression over here, if you look closely, the expression is something like this: sine of phi over phi, which in the mathematical term is known as a sinc function or a sampling function. So C of k can be written as a tau Tp sampling of pi f naught k tau. Now, diagrammatically, what does the sampling function looks like? Sorry. If this is the frequency axis and this is the value of k, we get the envelope of the function to be something like this. This is the envelope of the function, but we will not get a continuous value. We will get for every samples, because k over here is not continuous. K is always integer. And henceforth, we will get various samples of this function over the period of time. And similarly in this side as well. Now, what about the power density spectrum? If you recollect from the previous videos, we have studied the Parseval's relation, where we got the power density spectrum of a periodic signal to be something like this, which is modulus of ck squared, and this will yield the value of a tau over Tp squared when k equals 0, and a tau over Tp squared Sa squared of pi f naught k tau when k is not equal to 0. Now, what is the value of this peak over here? In the sampling function, this peak over here is nothing but this magnitude, a tau by Tp. I forgot to tell you that, so I went back and said it. Now let us realize what does the power density spectrum looks like. Now, the square of a sampling function looks like this. Which is also an envelope function and not continuous, as k is integers and k is an integer value, so we'll get various samples like this, but not the whole value. The difference between this and this function is that there is a negative part in the sampling function. In the sampling squared function, there is no negative part, and the whole function is in the positive direction of the y-axis. So I think we have understand about the power density spectrum of this rectangular pulse train that is given over here, and I hope that you will be able to solve for the previous functions that I have shown, the power density spectrum, or rather, if you cannot even draw the graph, you will be able to write down the equation at least. With that, we come to the end of our second problem and the second part of the video. We'll start, the first part of the video ends here.